I'm working on getting these things posted. It's getting there. I actually did post it already, but that first recording I think cut short or something, so it's real short. Okay, so periodic trends. So one of the periodic trends was radius, and we know the smallest ones are in the top right-hand corner. Right? The other periodic trend that's important for this class is electronegativity. So when we're talking about electronegativity, just definition, right? It's the attraction of an atom for electrons in a bond. And it is related to the radius, it's related to the ionization energy and the electron affinity. You put all those things together, and all points towards, again, the top right-hand corner being the most electronegative. So if you look at the electronegativities on this chart, it's really faded, huh? Yes. Fluorine has an electronegativity of 4. That's the highest electronegativity in the scale. And then lithium has, it was designed this way. Lithium's defined as 1, and then everything else is scaled in proportion to that, lithium being 1 and fluorine being 4. So that's why they're so nice and evenly spaced across that first period, 1, 1.5, 2, 2.5, 3, 1.5, and 4. That was Pauling's idea. There's other electronegativity scales that kind of all say the same thing. Okay? So if you have two atoms that are bonded, and we're going to draw some Lewis structures and sort of do this. Okay. We're going to draw LiH, Lewis structure for LiH. Now, we haven't talked about this, but lithium has how many valence electrons? We haven't done any of the metals. One. And so it wants to make one bond if it's going to make a bond. All right, so if we're going to do LiH, we're going to do something like this. And you should be familiar with the idea hydrogen wants to make just one bond now. So H2, it'll look like this. And then HF will look like this. And then we're going to do Lewis, but if I was doing a Kekulé structure, I wouldn't even draw the dots, and it's just so much easier. But I will continue to do that for a while, and then after a while, I'm just like, electrons? What electrons? Let's just draw these things. Okay, so go back for just a second. And lithium and hydrogen, which has a higher electronegativity? Hydrogen, as you go up, it increases, right? So that's a good way to remember it, although hydrogen's a weirdo where it's at.
It's supposed to be on the other side.
Yeah, it's supposed to be on the other side of the periodic table. I won't tell my story.
Maybe it doesn't fit like well.
I think it might be this room and the Wi-Fi cuts in and out.
The Wi-Fi doesn't even work on my phone in this room.
Oh, maybe it's your phone. Okay, so how many groups? You said 4, right? So that means this is tetrahedral. But there's another name for it. It's called a trigonal pyramid.
Pyramidal? I thought it was pyramidal.
So go ahead if you want, get your tetrahedral out, and then put 3 things on it. You know, preferably all the same things. So if you're not counting the electrons, it looks like a little tripod, like for a camera. Like a really small camera, but yeah, camera. Maybe like a GoPro tripod. So it's going to look like this. That's the actual, we call the shape. What it looks like if you ignore the lone pairs. So it literally looks like a tripod. I know it's hard to see. There's a bigger kit, but I think it's in somebody's office. That's a trigonal pyramid. Like a square pyramid is what you see in Egypt. It's got the base of it's square. This is a triangle shape. So that's a trigonal pyramid. those bond angles haven't really changed much. They're very close to 109.5. In ammonia, that bond angle, you don't need to know these details, is slightly small. Well, you need to know this detail. This bond angle is 107. And the reason is because the lone pairs of electrons, because they're not bonded to anything, take up more space and they push everything downward. So lone pairs occupy more space. So the space that's left for the bonds is smaller. Okay? So let's do another one. Let's do water, H2O. It's going to look like this. There's H2O. How many groups?
Oh.
Still 4. Turns out it's still 4.
I think we'll forget to count the letters.
But here's the thing. 2 of them are lone pairs, right? So now you just pull one more off. These groups still keep their same orientation relative to each other, roughly. But this is for water. And the shape, it has a name, it's just bent, right? So we call this tetrahedral and it's bent. Questions about this? So far so good? Let's do NO2.
Sorry.
Oh yeah.
So
Yeah, stop me anytime you have questions.
So for water, it would still be 107 degrees in between the...
It's actually 104 because it has another lone pair, it takes up more space, and then it squeezes what's left down. Yeah, so it's 104.5. But as far as I'm concerned, if you say less than 109.5, that's all we need to know. Yeah, the actual angle depends on whether or not, like if you put fluorines on there, for example, instead of hydrogens, the angle grows because the fluorines repel more. Everybody has these numbers, 109.5, 107, 104.5, all fixed in their brains, but that's only if it's hydrogen. If you change the atoms, then they take up more space. Like if you put IOI, so I2O in there, the bond angle is like 130 degrees. It's way bigger just because the iodines are so big, they just push apart from each other, right? So, yeah. So just remember less than 109.5. That's the lie everybody believes. So let's go with that. Is that a lie? I don't know if it's a lie or not.
No, I think
It is. So NO2, we're going to do NO2. Let's see what you get. I do Lewis structure for this one, just for fun. And I'll put a formal charge here. That's what it looks like.
But it's a negative.
Huh?
It has a negative on it.
Yeah,
Yeah.
I put a negative on it. And then this is what I want to know the shape of. So how many groups on that nitrogen? 3. 3 because we're only counting, this is 1, that's 1, and that's 1. It's not like doing like valence state or trying to calculate formal charge. It's just a number of things that are around the atom. It doesn't matter if it's single bonded or double bonded. Okay? So I have 3 groups. And then going back to what we saw previously, that bond angle, that grouping is trigonal planar. So if you think about the molecule that you had before with the brown atom, oops, I did it too, wrong hole. Looks like that, right? Except one of the groups is a lone pair. So what do you have to do? Just pluck it off. That's what it looks like. It looks like that. And this thing, unfortunately, is also bent. So when we talk about the name, for this one, we have to say trigonal planar. And it's bent. The angle on trigonal planar is about 120 degrees. This one is still about 120 degrees. If you really want to know what it is, I have a website link I could share with you that basically takes all kinds of structures and they actually analyze some molecules using a technique called X-ray diffraction and determine the actual angles in the molecules. It's for really like nerdy, like, gee, is it really 109.5? And you get to look at it and you go, it's not. And you feel all happy for some reason. I don't know.
That sounds fun.
You like to break science. That's the way you do it. You actually look at data. Okay, the last one. That's actually acetylene. You're going to end up with something like this. All right, each carbon has 4 bonds to it. That's the way you get it to have 4 bonds. By the way, do you like that way of drawing loose structures better than the way you learned before, or do you like the other way? Because you can do either. I have the instructions for the other way in the back of the notes. I'm just not going to go over it. I just like, oh yeah, it looks right. All right, we're going to look at the shape on that carbon, which will be the same as the shape on the other carbon. How many groups? 2. So this is 180 degrees. All right. And you notice I drew this one as 120. I wrote this as 120, but I drew it as 90. That's usually what happens. People, when they draw them, usually put things at right angles. When you actually try drawing these in the future, if you know that it's trigonal planar, try to draw it at 120. Right? Just get in the habit of seeing things for the shape that they actually are. It's still recording. I don't know why it stopped before.
So that was
Okay, so this is a summary of the shapes that you'll see. Okay, for trigonal planar, you have trigonal planar and you have bent. All right. For tetrahedral, these are all the stuff that I talked about on the previous slide. For tetrahedral, you have the tetrahedral shape, you have the trigonal pyramid shape, and you have bent. Right. Water was the example for us here. H2. Oh, sorry. Let me go back. H2O, this was the NH3, and if you want an example of this, try doing CH4. For trigonal planar bent, we did NO2 and minus, and for trigonal planar, did we use just a straight up trigonal planar? I did not, but if you want to do a trigonal planar that's not too bad, do carbonate ion. It's going to look like this. Oops, sorry. I meant to put a C there. That's what carbonate looks like. It's got 3 groups, and that's trigonal planar. So this angle is 120 degrees. If you have a model kit, great. You don't need to have a model kit. One of the standard things that people do is they find their favorite candy and toothpicks, and they build models out of their favorite candy and toothpicks. And then they eat them when they're done. Just take the toothpicks out, and you're fine. Okay. Okay, so we want to talk a little bit about molecular polarity, and we're going to go back to the model kits here in a second, but bonds can be polar, right? So for example, like HF, that's something it's a polar molecule. Kekule drawing, right? I left the lone pairs off. Or HCl, those are also polar. And if you want to know whether or not the molecule's polar, there's only one bond, so that has to be polar, right? This side's dipole's going like that. This one, the dipole's going like that. But if the molecule has more than one bond in it, you have to consider the shape. So, for example, right, looking at let's say NH3. Well, actually, Yeah, let's do NH3. Let's build this thing again. Right? First of all, if you look at the electronegativities, this bond is polar. There's a difference in electronegativity. Okay? But if you actually build it, I'm going to leave the things off. Make NH3, it looks like this. And then don't put the lone pair in. One of the things that you can see, right, is that this bond is polar, so this is the nitrogen right here, right? That side's negative. And then it's negative here, and negative here, and negative here. So the positive end of the molecule is this whole side. And they're all equally positive. So if I'm looking at NH3, right, think about that. And I'm thinking about the dipole of the molecule. Like, which way is the charge separated on this molecule? This side of the molecule, the whole thing's positive because each one of these carries the same amount of charge. That means this side is negative, right? It's all accumulated right here. So the dipole for this molecule is polar. The dipole goes like this. Goes straight through the middle. So the shape of the molecule, right? If you want to know whether or not the molecule is polar, one of the things you have to consider is shape. And when you look at the shape, you can tell, like, oh, all the charge is on this, negative charge is on this end, all the positive charge is on that end. So it's important that you visualize what that looks like. Let's look at CO2. Again, Kekule structure. CO2, you can do a funny thing. You can do bendy bonds. And you take a carbon, and you take these big bendy bonds, and you have to grab 4 of them. And oxygen is red. So put 4 of these on the carbon, and then take 2, doesn't matter which 2, attach it to an oxygen, like this. That's a double bond. All right? Now, is that polar or nonpolar? Right? Well, oxygen's really high in electronegativity. It's on the top right hand of the periodic table. So it turns out this bond is polar. If you look at your electronegativity chart, you guys have it in front of you. But oxygen's 3.5. Yeah, oxygen's 3.5 and fluorine's 4. And I only remember that because Lewis made it even, like 1, 1.5. So I just have to think about where it is on the periodic table. I'm going to take this one, I'm going to attach this. Attach it like this. What is that shape? It's a linear, right? It's linear. So think about this. This carbon is the lower electronegativity, and the oxygen's high, so there's a negative charge over here. But over here, again, this oxygen over here, it also has a negative charge. Now, in order for a molecule to be polar, the charge from one end of the molecule to the other has to be different. But in this case, this is exactly the same as that. And so this is actually nonpolar. So when we look at carbon dioxide, right, even though it has polar bonds, when you take into account its shape, the molecule is nonpolar. The distribution of charge is exactly the same on both ends of the molecule. Now, there's more electron density out here. That's still true. There's more electron density out here. But the distribution of electrons is uniform, and so it's nonpolar. So for CO2, right, you could write it like this. This is partial negative. This is a partial positive. But this is also a partial negative. The molecule is nonpolar. And that's because the molecule is symmetric. And that causes an even charge distribution. Questions about that? got to kind of build them to look at them, right? Got to build them to look at them. And like I said, you don't need to have the fancy kit. If you have, people do it with marshmallows. It's the easiest one. You stick a marshmallow with a toothpick, and then you put 2 marshmallows on either end. Get the small colored ones so that you have, like, you can represent the color scale. Right? By the way, that makes good bait for trout fishing too. Just saying. Use it to float salmon eggs.
Could you move it up? Does it say open charge distribution?
I cannot move anything up.
Okay, there you go. It's fine. I know what it says now.
I kind of want to do that. It used to be that in these rooms, the projectors shot right onto the screen, and you could just write on the screen. But this is actually better. This is my version of sorting. All right, any questions about that stuff? So this is kind of a dicey topic because if you only had 3A, you didn't get this. And so I'm going to try to go through this carefully, but it is stuff that some of you haven't seen. Let me get my notes too so I can look through them as I go along. I have more notes for you today, by the way. So, kind of one of the unsaid things in intro chem is that when you make a chemical bond and we do all these Lewis structures, it has to happen through orbitals. So we have atomic orbitals, we have s orbitals, and we have p orbitals, right? And then there's d and f, but we don't care about those for this class because for OChem, for the most part, we don't ever see them. So when you think about an s orbital, right? And I mentioned this before, like a 1s orbital and a 2s orbital largely look the same. On the inside, the 2s orbital looks different, actually, but it doesn't really matter for us. It looks like a sphere. Right? Inside details, though, are different. So, for s orbitals, they're spherical. For p orbitals, these are actually not what they look like. This is what they call a stylized version of it, just to give you a better sense of direction. Do you guys remember ever playing Super Mario Brothers?
Yes.
And you know the little mushrooms that run around, little mushroom cap guy? Mm-hmm. Yeah. That's actually more what like if you were to draw a p orbital, the top of it kind of looks like this. Right, and then for the mushroom guy, it was like, kind of like, right? Yeah. Right, but for a p orbital, it actually, the other side kind of looks like this, actually. So it looks like you ripped the bodies off 2 of them and stuck them together. Sorry.
You killed them.
I killed them. They killed 2 of them to make a p orbital. That's how valuable they are. So that don't let the sacrifice go in waste. So this guy here kind of is what that one is, right? But we stylize it so it's easier to see. Right? But it does make some of the later explanations harder to understand when we talk about like double bonds. Okay, so I wanted you to understand that they're actually not these really skinny, narrow things. Our society is obsessed with skinny, narrow things. I'm not one of those things. Okay, I'm just saying. The other thing that you have to sort of get over is the idea of hybridization. In order for an atom like carbon to make bonds with its orbitals, it has to mix its existing orbitals up to get new orbitals out. So just to give it a context, right? Carbon's orbital diagram looks like this. And there's the 2s, and then there's the 2p's. And if you're just looking at the valence electrons, which I'm doing here, carbon has how many valence electrons? It's got 4, right? So it's going to put 2 electrons in the 2s, and then it has to put an electron in the 2p like that. And that's the way it does it. And I don't care that you know the rules for this, but here's the basic idea. Unless carbon does something to fix the situation, it only has 2 electrons to make bonds with. That's kind of the idea. If you put the electrons in the orbitals, and we are committed to the idea that bonds take place through orbitals, carbon can only make 2 bonds. But in fact, we know, like the simplest carbon molecules we know are like methane, and it already makes 4 bonds. So what it's going to do, what carbon ends up doing, is saying, well, scrap this idea. Let's make them all the same, and it does what's called hybridization. And hybridization is shown here. So what it's actually done is it's taken the p orbital and then the s orbital, and kind of like Play-Doh, just made new orbitals. Okay? And I'm not going to go into all the details of the mathematics or even like the symbolic mathematics that does this. Basically, you end up with one side being larger, and this is known as the bonding side. And remember I mentioned lobes before. It's the bonding lobe. And one of the things that hybridization does is it makes bonding more efficient. The other thing that it does, though, when you hybridize these things, and you just got to take this on faith, basically, the bond angle becomes 109.5. P orbitals are 90 degrees apart from each other. So if something really bonded, like going back for a second like this, right, these are the different p orbitals. There's the px, the py, and the pz, and I mentioned those the other day. But if you really were going to bond through those orbitals, things would have to be 90 degrees apart from each other. And that's really close. That's less than the 109.5 of a tetrahedron. It's less than the 120. It's less than the 180. So really, just the repulsion forces those things to be further apart, and that creates new orbitals. Okay, so back on this. My bond angle is going to change, and it's going to be 109.5. The hybridization is going to be sp3. So if I'm going to make methane like this, right, I'm going to take a carbon, put 4 groups on. You've kind of already seen this already, but I'm just going to go ahead and do it. Ooh, I got a purple one. I don't need a purple one. Unless I have all 4 purple ones, then I can. Purple's a good color.
It is.
I grade in purple. I have red too.
Purple's my favorite.
Yeah, purple is probably my favorite color. Kind of a weird color though. It's kind of not any real color. It's kind of like blue, but it's not.
It's kind of like pinkish purple.
Yeah, that's the weird part. Okay, so that's the 4 groups, right? That's the tetrahedron that you get when you do the hybridization. Now, hybridization is based on number of groups. The number of orbitals that hybridize is based on the number of groups. Ooh. So I have this stupid trick. Who had their Sharpie marker? This is awesome. They usually do it black. This is silver. I'm going to take my fingers, and I'm going to put an S on this finger. And then I'm going to put a P here, and a P here, and a P here. And we're only worried about S and P orbitals, but if you had D orbitals, they go on this hand, okay? And so if I ask you how many groups there are, and you need to know the hybridization, and it's the stupidest trick ever. What's the hybridization? S, right? P3. That's the hybridization. Now, let's say there's only 3 groups. And this is going to be important when we start talking about double bonds and triple bonds. Let's say there's only 3 groups. Okay. What's the hybridization? sp2. How many are unhybridized? 1. It seems so stupid, but it's just like, it works every time. It makes me really happy. The other reason I do this is one of my favorite students from many, many years ago, she came up with this as she was tutoring, right? And she said, oh, that's a great idea. I'm stealing that. She went on to get her like PhD in biochemistry and all that stuff. So she went to UC Davis. She was one of those students that was like, oh, I don't think I'm going to make it, and I'm not going to be a good scientist. I had to, you know, give her a little encouragement. She went to UC Davis. She gave the commencement speech. She was kicking some butt. And then graduated from there and then ended up working and doing her PhD at Davis. And kind of just went straight through. And now she works for, what's the name of that? Genentech? The big pharmaceutical. Yeah. So I actually have a couple of students that work for Genentech. One's like in management. She, like every time I see her Facebook posts, like, oh, I'm in Taiwan. Oh, I'm like, crazy. She wanted to be a nurse originally, I think, and then she went on, got her degree, and then she, just right out of school, she just went straight to Genentech, went to hiring fair, and she got in the business side, even though she had a biology degree, I think. Yeah. It was a lot of fun. I'm watching my children grow up.
Isn't it feel great that they succeeded and you taught them?
Yeah, that's a good thing. Okay, so let's talk a little bit. We'll talk about the bonding in ammonia, okay? And we're going to draw its Lewis structure again. You guys may just have it memorized by now. This is what happens to chemistry teachers. We just have it memorized. Okay. Nitrogen has to make 3 bonds. Hydrogen has to make 1, so I end up with that. So how many groups are there? What's the hybridization? SP3, yeah. Say the S first, and then you say P, and then you go like this. That's SP3.
Wait, what hand are you using?
Doesn't matter. What hand are you using?
Because like your hand.
I'm right-handed, so if I'm writing, I have to look at my left hand. If you're left-handed, you put it on your right hand, so you can, yeah, see? When we think about these orbitals then, the nitrogen is using an sp3 orbital, right, to make a bond to the hydrogen. Now, hydrogen is small. It's a 1s orbital. But those are the orbitals in the bonding. The angle is 109.5 still. Less than 109.5, really. I'll just do that. 107. And the lone pair? The lone pair is in one of the hybridized orbitals. Okay? So that's a simple description. Now, let me ask you a question. Okay, as a percentage, right? What percentage is an sp3s?
25.
25, because like it's one of the 4 fingers, right? If it's sp2, what is the percentage of
33.
S? Yeah, 33, and then 50, right? The percentage of S hybridization changes with the level of hybridization. The fewer P's you put in, the more S there is. Now, here's the important thing. That affects how these things react. It affects their properties, right? S orbitals are short, or small, right? The more S-like it is, the shorter the orbital is, and that changes its properties. How it behaves in chemical reaction depends on its hybridization. So I'm introducing that idea now because it's important to understand. I'm not just doing this to torture you with a new idea you've never seen before, okay?
When I would do the SP3, I would just count SPPP and then
Oh, yeah, I like this better.
sometimes
I hate saying PPP over and again because I have 5 boys, and you have to teach them things like you wipe the toilet even if you didn't miss, because there's PPP everywhere. PPP. Yeah, I was just thinking about the things you have to tell boys as they're growing up that just.
You didn't have girls?
Well, I was raised by my dad. Passed when I was really young, so I was raised by my mom and my grandmother. So I always say I was raised by a pack of wolves. But yeah, I have like a completely different set of like when I saw what other guys did, I was like, what? What, the toilet seat is actually up? What? Yeah. And half the time when we went pee, we just went outside. Because I was on a farm, right? And we had trees all around us, and that was the thing to do. Bathroom's busy? I'll find someplace.
Find a tree.
Find a tree. Okay, so we're doing ethylene. Sorry. TMI. Ethylene looks like this. I'll just draw it for you, and we'll talk about hybridization. And I'll try to draw the bond angles fairly faithfully, but it's a trigonal planar on both sides. So this carbon, right, hybridization is 3 groups, sp2. Yeah? See how easy that is? You don't have to think. It's 3 groups. You only need it for like a day or two, but then it's just kind of fun to draw on your hands again, because you used to do it when you were in elementary school, then you grew up and that became uncool. My new Stanley Starbucks cup, very fancy. Yeah. It's one of my children. They just left it at the house, so I don't even know where it is now.
It's yours now.
It's mine. I can't afford that. I don't know how they can afford it. These are the ones that like are in college and graduate school, right? They just leave crap like this around. I'm like, that's cool. I'm like, I don't know where it went. So here's the deal. This is what the hybridized bond looks like here. Okay? That's my hybridized bond between the 2 carbons. This is trigonal planar. So when you're thinking about what that looks like, I can build that with 2 bendy bonds like this between the 2 carbons like that. And then the hydrogens have to be attached to the hybrid orbitals. Kind of hoping to go faster, but I think we're going at an okay pace. You guys keeping up okay? Not like horribly tired or horribly bored or tired of my stupid jokes yet? The stupid jokes you can't really do anything about. Okay, so that's what it kind of looks like, but you notice something about the molecule? It's completely flat. It's completely flat. Because this is sp2 and this is sp2. Now, here's the thing. When I have a double bond, right, you can see, like right here, there's a single bond here. This kind of bond that goes directly between atoms is known as a sigma bond. The double part of the double bond is made from, remember when we do sp3, right, or sp2, there's one unhybridized p orbital? The double bond part of the double bond is made with those p orbitals. So this bendy bond across the top and across the bottom is the 2 p orbitals coming together to form that bond. So it's literally, that's a p orbital there, that's a p orbital there, and then they overlap in the middle to form a bond. Now that bond is not on the axis anymore. It's like this. Okay? And if that molecule tries to rotate, like with one end versus the other, that bond keeps it from rotating. And the only way you can get it to rotate is by breaking the bond and then allowing it to rotate. Good example, Ismark, here, come here. I know you're not horribly embarrassed by me, so we're gonna dance. Well, okay, old person dancing. Okay, so single bond, twist. Da, 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 da. Very easy, right? Okay, now we do double bond. Double bond, twist. Yeah, that's right. You can twist a little bit, but now this is what happens. This is the way the pigments in your eyes work. Light hits one of the bonds, breaks, twist, and then reconnects, and then your eyes detects light. That's how it works. But you can break the pi bond, but the sigma bond is still connected, and you can spin around. Okay, it's called a change in conformation, change in the shape. Again, these things are really important for understanding how things work. But when you have a double bond, you have a sigma bond and a pi bond. So this is the pi bond. You can't. I mean, it says pi bond in little sigma and pi in small letters. This is the sigma bond. This bond is right there. It's inside that. So those are like superposition images with part of it not shown in each. So what you're not seeing in here is this, and what you're not seeing here is this, and then you stick it all together and it looks like that. And the pi bond is, this is an important thing about pi bonds, they're more reactive because the electrons are on the outside of the molecule. I'll just make it a little short. Because outside. I'll just say out because I'm out of space. Because they're outside. You can probably fit it in on your paper. I can go like this. Outside. And I'm out of space. Just fill in the. Not only is the E silent, it's invisible. Sorry. Okay, so just a quick summary. I was thinking about the P is silent joke. You guys know that joke? Why can't you hear pterodactyls in the bathroom? Because the P is silent. I have kids, what do you say? I've had some really horrible jokes told to me by my kids, and you try not to laugh. You're like, I can't laugh at that.
Yeah, like my nieces and nephews are not supposed to laugh.
It's like the knock-knock jokes where they just, because they learned the name of an anatomical part of the body, so they'll say knock-knock, say who's there, and then they yell out this part of the body. You're like, okay, that's not funny. You just can't help it. You just end up laughing like crazy. So a triple bond, okay, get back to triple bond. What's the hybridization for a triple bond? So let's look at this. I'm going to draw you triple bond. Looks like this. So like acetylene was our example for the triple bond, but anytime you see a triple bond, what's the hybridization of carbon? There's two groups, so it's sp, right? It's sp. How many unhybridized p orbitals are there? Two. Those are the ones that make the pi bonds. So when you have a triple bond, right? A triple bond is a sigma and two pi's. Because who doesn't like pi? And again, as I said earlier, right? sp3 is less s character, is what we say. And a triple bond is more s character. And that will affect its chemical properties. When we talk about acids and bases in the next chapter, hybridization of the atom becomes important.
So is on the triple bond, is it supposed to be sigma equals pi plus pi? Because it just says pi, sigma plus pi. For the triple on the left side?
Oh, yeah. Over here, yeah.
Oh.
Sigma plus pi. There. Again, copy and paste, fill in the blanks. Good call. All of a sudden, it looks the same. Because it is the same on the slide. All right, that's kind of it for that chapter. That's all the chapter, I think. But I'm not done. I want to mention one other thing that I didn't cover in the chapter, but I really want to talk about. So what I'm going to do is make one more blank slide, and this will be all I have to say for today. Okay? And it has to do with resonance. So when you're drawing a Lewis structure, invariably you're going to come to a situation that looks like this. And when I do resonance, I have to draw in all the electrons. That's what I'm going to draw. And then you're going to say to yourself, I wonder why the other oxygen isn't the single bonded one. Why isn't it like this? And the good answer is there is no reason why it wasn't. In fact, it could be drawn both ways. And these structures that can be drawn multiple ways, okay, by only moving the distribution of electrons are known as resonance structures. And we'd separate them with a double-headed arrow like this. And these are resonance. Resonance is important because one of the things when you see resonance, you know, is that it's more stable because it can move the electron charge around. So resonance, if a molecule has resonance, it distributes its electrons and is more stable. Okay? Distributes electrons and is more stable. So I'm going to show you an electron arrow trick. Okay? So you can convert from one resonance structure to another by using arrows to show where the electrons are moving as the new resonance structure is formed. And this is officially known as arrow pushing. Like I'm an arrow pusher, and you are wanting to buy some of my arrows. I don't know. So this is what happens. Start on electrons. Okay, so I'm going to go like this, and then you go like this. Move it to where the bond goes. Okay, so when I do that, though, if I were to put that in there, that nitrogen would have five things, right? It would have like 10 electrons. It would have 2 double bonds. So what I have to do is I have to break another one. So you can start the opposite, start on a bond and then move it to an atom, okay? And you'll notice how this fits together. Like this, right, over here, that's going to become my double bond, and I'm showing that by having this pair of electrons moving into here. And this is going to produce a single bond. I'm only moving 2 electrons at a time. You can't do more than that, right? In a bond. You can't move you can't move the whole double bond out. And so now I'm taking this and I'm moving it to the atom. And then you end up with the structure that's on the right. So on your worksheet, if you flip to the very last section, there's like a whole page on pushing electrons, okay? And then there's a whole bunch of examples of pushing electrons. Like you're supposed to, in the bottom here, I just want to point this out, you're supposed to add the electron arrows to show how the electrons are pushed. And then there's some practice where you actually have to draw the other structures and then push the electrons, okay? So what I want you to do is I want you to do the worksheet. But this is for discussion. You'll turn it in, you'll get points. It's like a credit, no credit thing. Could be right, could be wrong. I like it to be right, though. We're going to discuss these. So I want you to try doing these. It's a very important thing to understand as we go on through the semester. It's one of the biggest things to understand in organic chemistry. So pushing electrons.
Pushing your arrows to the
Okay, I'm giving you 2 minutes to ask questions or leave.